Experience the power of concurrent engineering for end-to-end wire harness design. Leveraging the best-in-class solutions for model-based systems engineering, MBSE, and detailed logical and 3D wire harness design, all within the 3D Experience platform. The overall process is made up of 8 steps. This short video will cover each of these steps at a high level. Don't hesitate to reach out to us for more detailed demonstrations. Let's meet our team for this demonstration. We have 3 systems engineers focused on master equipment, logical architecture, and 3D systems routing. Our electrical engineers focus on avionics and detailed wiring data. And our harness engineer focuses on 3D harness design and manufacturing preparation. You can see their tasks on the left in blue and the value of those tasks on the right in green. To begin our brief journey today, the Systems Engineer Master Equipment Specialist will log into the 3D Experience platform and search for and open a CATIA Magic Cameo system model. Note that the application opens on her computer, but directly accesses 3D Experience. In Step 1, she will establish system references between the logical system model and the 3D model. First, she synchronizes requirements from 3D Experience to our system model in CATIA Magic Cameo. The Data Hub opens the authoritative requirements in 3D Experience and enables them to be synchronized into the system model. This ensures that the system model will be developed from the same authoritative source of truth for requirements in 3D Experience. Next, she defines logical connectors that match the physical connectors used on electrical equipment. From those logical connectors, she builds up logical equipment definitions that use those standard connectors with specific signal functions at each pin. To match the logical equipment, she and her team will define corresponding 3D representations in 3D Experience. These are referenced in the system model and linked to each logical equipment definition. Finally, our systems engineer opens a space allocation model of our overall air vehicle. You can see an exploded view of these spatial zones here. These zones will be used as references for the spatial placement of electrical equipment in 3D and within the CATIA Magic Cameo system model. Now we have all the references we will need to design a complete solution, and we can move into Step 2 for solution-specific architecture. In this example, our logical systems architect has created the top-level eVTOL system, its electrical subsystems, and their constituent parts. Each of these parts is defined by the logical equipment and its connectors that the Master Equipment Specialist created in Step 1. As the Logical Systems Architect defines instances of equipment, he also allocates them to intended spatial zones. The Logical Systems Architect transfers this architecture to 3D Experience using the FLXML protocol, ensuring digital continuity from the system model to the detailed electrical design. You can see the equipment, connector, and signal definition exactly as specified in the system model, with consistent element IDs to maintain continuity. With the logical equipment now in 3D Experience, the 3D Systems Engineer can concurrently develop the physical placement in context of our system model. He places 3D equipment, synchronizes it, and verifies traceability based on the relationships defined in our system model. The Logical to Physical Assistant tool quickly reconciles the links between the system model content and the 3D content. It also shows whether 3D equipment placement is within the zone specified in the system model. Any missing equipment can be automatically placed in the zone as specified. Here, the 3D systems engineer has placed the magnetometer, adjusts it inside the zone, and rechecks its compliance. Finally, the 3D systems engineer reviews the implement links between system model content and 3D equipment. You can see here how the 3D equipment implements each logical instance of equipment. Any of the team can review these links within the 3D Experience web application, Systems Traceability. Here, one of the systems engineers has created a systems traceability scope. She navigates the system model in CATIA Magic and adds the top-level system to her scope. She also adds the 3D Experience logical content created by FLXML and the 3D physical content. Now she can inspect the traceability at an element level to see the digital continuity all the way from system architecture through into 3D physical design. She can also cross-highlight with a 3D view to see the 3D elements in spatial context, so that she can ensure the consistency of architecture and detailed design, and perform impact analyses for change assessments. Once we have the architecture developed in the logical system model and in 3D, we can move into step 3, where we define electrical connectivity. In the system model, the logical systems architect or the avionics engineer define electrical block diagrams specifying connections between each piece of equipment in the logical architecture. She creates these connections, or net groups, to form the basis for cables that will carry shielding and twisting specifications and detailed signal information. Concurrently with the electrical block diagram definition, the 3D systems engineer defines pathways to reserve 3D space where wire harnesses could be routed. With these pathways, he defines a 3D network of how signals can travel between equipment, and also how critical signals must be segregated and separated. Back in the system model, the avionics engineer is building the detailed pin-to-pin connectivity. Every pin has direction and signal types to ensure that incompatible signals are not inadvertently connected. She can also utilize the AutoWire capability to automatically make these connections, saving time and error. In step 4 of the process, we synchronize our system model to 3D Experience and generate the schematic net diagrams. The avionics engineer uses the FLXML protocol to transfer the electrical connectivity definition from our system model, maintaining rigorous traceability into the 3D Experience platform. You can see the original architecture of equipment instances together with net groups and nets from her work in the system model. She validates electrical connectivity at the level of an individual net, or in a system-level customizable report that shows each connection. Finally, she automatically generates net diagrams as a visual schematic representation of the equipment, connections, and signals in the model. In Step 5, we will see the concurrence of electrical connectivity in logical and 3D as the logical nets become 3D signals in an automatic, optimized network of 3D signal routing. With the logical net groups and nets now in 3D experience, the 3D systems engineer transforms the logical nets into unrouted 3D signals. You can see the straight line connections between instances of 3D equipment. He now performs signal routing to develop an optimized 3D network to find the shortest paths, respecting pathway fill ratios, EMI compatibilities, and segregation requirements. The pathway fill ratios can be visualized with a customizable color scheme. In this example, fill ratios above 50% are colored red, and fill ratios below 20% are green, with yellow in the middle. Individual routes can now be inspected and visualized. Manual routing can be performed to modify the results of the automatic network. Step 6 combines the net data with the 3D split signals to generate detailed wiring data and diagrams. Much of this process is automated, thanks to the underlying data model and compatibility tables. Our electrical engineer reviews the net diagram from CATIA Magic from Step 4 and the 3D routed signals from Step 5. The 3D routed signals have also been split wherever they pass through an interface volume, representing a production break or other location that will require disconnects in the signal path. Using the 3D split signals and the nets, the electrical engineer now runs the net-to-wire process. This transforms the abstract nets into detailed wires between equipment connectors and disconnects, maintaining the detailed specification from CATIA Magic, such as signal and wire gauge. The net-to-wire process automatically instantiates harness connectors at equipment, logical wires, logical cables, and shields. Disconnects at interface volumes are temporarily defined as generic until a specific connector is assigned by the electrical engineer. The preliminary wiring diagram is auto-generated using the net diagram as a template. You can see the defined connectors in solid line type at the equipment and the preliminary disconnect in dashed line between the equipment. The Wiring Definition Assistant tool shows the number and gauge of wires that need to pass through one or more disconnects. The electrical engineer selects a compatible connector from a library, and the Wiring Definition Assistant reports that all wires can be accommodated in this connector. Now the electrical engineer allocates wires to each pin or socket of the connector, either through the table view or the 3D face view of the connector. The mating connector is automatically selected, and the allocations from the first side are made available and accepted onto the mating connector pins or sockets. Now that both sides of the disconnect are defined, the electrical engineer regenerates the diagram from the underlying model and replaces the temporary names of the disconnect with the final names. Thanks to the relationships built into the underlying data model, the electrical engineer can review the allocation of each wire to its harness and the traceability of each wire to its original net. Finally, part numbers for compatible cables are automatically filtered and assigned, and part numbers for compatible contacts are also filtered and assigned. Step 7 synchronizes the logical definition from Step 6 with the 3D routing and finalizes the 3D harness design. The wire harness engineer reviews the 3D content, and since bus B2 is already complete, he will specify bus B1 for further detail. He uses the Logical to Physical Assistant tool to compare the logical contents against 3D contents. This tool automatically places electrical parts in 3D with electrical connections to corresponding equipment ports and mating harness connectors at disconnects. All cables and wires are also instantiated in 3D with correct from to and diameter and bend radius information. The wire harness engineer routes the harness bundle through clamps and updates the bundle diameter based on cable or wire inside the bundle, returning cable and wire lengths for manufacturing and analysis. Step 8 takes the fully defined 3D harness and prepares it for manufacturing through flattening, auto-generated documentation, and formboard definition, all within a consistent user interface. In the electrical manufacturing preparation workbench, the wire harness engineer creates a flattened model that is fully synchronized to the 3D harness. A manufacturing diagram is auto-generated and populated with connector face views and pinout tables as per the standards of the organization. The harness is now ready for manufacturing and formboard definition. We hope you have enjoyed this short tour of the end-to-end model-based wire harness engineering process, leveraging the best-in-class tools for MBSE and 3D wire harness design.